Today I would like to talk about quasi-smooth intersection Mori spaces. I will try to make a historical motivation of why these spaces are interesting. Uh, but also I would like to point out why I got interested in this kind of objects because okay, I will do it step by step because I write them not for the same purpose that they originally started to be interested historically. Okay, so this is more or less the structure of the topic of the talk and the main topics. So I will start with the motivation. The motivation, as usual, in algebraic geometry started with Italian school, more precisely with Castelnuovo. Uh, he, uh, he found a way to avoid, let's say, some kind of very particular curves in algebra. They appear very naturally in algebraic geometry. So if you have a smooth projective surface, always, I will always talk about varieties and schemes over the complex numbers. And if you have a surface minus one curve, these minus one curves are the particular ones because they have this curiosity that the self-intersection is negative, is minus one. That for a geometrical, intuitive, particular point of view is very unnatural, let's say, but it has the same feeling that when you deal with x squared equal to minus one as the complex numbers, right? Doesn't have like geometric interpretation of the area of a square, but still has too much meaning in terms of algebra, and also you can go deep in many others geometrical objects. So if you have a surface and you have a curve inside that surface, Castelnuovo found a way always to contract that surface to a point, right? To find another surface, S prime. In such way, the surface is going to a point. Of the surface, except for the curve, a very classical objects in algebraic geometry, this kind of irrational morphisms that are defined only in open subsets, but with the Zariski topology. Okay, but this guy found a way to to avoid this kind of, let's say, annoying curves. And this is like the main motivation of what is the minimal model program, because many algebraic geometries try to do this for higher dimensions, but it's very difficult to find like the right notions, like the right concepts to apply the same techniques, or at least similar techniques, in order to do something like this in 3-folds and 4-folds. But in the 1988, Mori, a Japanese mathematician, found a way to define concretely and now very well behavior the right notions to run the same program, not only for surfaces that Castelnuovo and the Italian school did, but also for 3-folds. He introduced something that is called a flip. Somehow it's like behind all these things, there are something that is called the for differential geometers, the cotangent bundle. For algebraic geometries, a cotangent bundle where everything is smooth. You can relate this with a line bundle, and also you can relate with the collection of all line bundles form a group, what is called the group divisors. Okay, keeping all these things and trying to understand how they behave as very with the algebraic structure, you can run the same program but for 3-folds. And recently, let's say in 22, Hugh and Key found like the name saying too much, right? Mori dream spaces, like the definition for these geometric objects to run completely in a very well behaved nature, the minimal model program. So the idea is I will present two definitions. one like can get the feeling of the taste, how it is related with this program to avoid somehow these annoying curves or this object that has a negative cell intersection. So this is more or less the motivation, the historical motivation. Okay, so let's start with some definitions. So let me why a normal projective variety. This normal projective variety somehow is the extension of how to say this. It's like for curves, being smooth and being normal is exactly the same. So for higher dimension, normality keeps track somehow of what a smoothness is, but having some control in the singularities. Okay, we did not by N1 the vector space of Cartier divisors. Cartier divisors or divisors in general are these codimension one varieties inside the normal variety. In algebraic geometry, they have the behavior of a group when everything goes well, like when, for example, y is smooth. And the question with numerical equivalence is like you put in the same set divisors that intersect have the same intersection with all the curves inside your variety. So you have the collection of all these codimension one subvarieties, and you see how they intersect with curves. And if they intersect in the same amount of points with every curve, so you put it in the same class. Okay, this is N1. Okay, the NEFCON is the closed convex con generated by classes of NEF divisors. As I said before, like in algebraic geometry, is very common and is very and is well formulated and well understood how things intersect in a negative way. But the NEFCON only keep track of the ones like intersect positively. So this is the NEFCON. Just consider these Cartier divisors which intersect with curves in a positive way. Okay, the mobile cone is, by definition, is the stable base locus is of these divisors that has at least codimension 2. Okay, this is, let's say, a little technical, but what is behind is these curves like the intersect negatively. Somehow geometrically they are very rigid. It's like they don't come in families. It's like you cannot deformate them. But the movable cone are precisely these ones, like they are in families. You can, roughly speaking, do deformation. Okay. A small q factorial modification of the variety is a contracting birational map with another variety, which is cofactorial. Okay, and another thing it happens in algebraic geometry is like also makes sense to have things like intersect in rational numbers. So you can find things like this divisor, or this surface, and this curve intersect in something like is 1.5, and it's somehow measured like the singularities that the variety has. This being q-factorial means like if you have a divisor with this behavior, at least you can find an integer. When you multiply the divisor by that integer, everything is going to intersect as you expect, right? In an integer, in a natural number. Okay, so a q factorial modification is another variety. The rational, as I said before, is the morphism is defined in an open Zariski subset of the variety. Okay. Okay. Now I have everything to introduce what a Mori dream space is. So the first thing is the Picard. The Picard is like the collection of all Cartier. The Picard group is the collection of all Cartier divisors. The first condition is this Picard number is the collection of Cartier divisor quotient regular maps. Okay, it's like in the equivalent in complex analysis of being holomorphic. And you ask as a first condition that this way to characterize divisor or make classes of divisor coincide with the numerical. The numerically, remember, is like you put a divisor in the same class if they intersect in the same way with all the curves inside your variety. Okay, you ask like the ones like intersect positively also to be finally generated for semi-ample divisors. Semi-ample divisors are the ones like allows you to make morphines from your variety, no more be rational more or rational morphines from your variety to projective spaces. It's like a less condition as the name said of ampleness. Okay, and this way of doing modification of your initial variety has to stop it at some point. There are only finitely many. As you see, it's like you are doing somehow like Castelnuovo did for surfaces, because as you can see here, the dimension is important. It's like you can run this for any dimension. Now, the problem I imagine when they introduced this almost 20 years ago was to find interesting examples, right? So after that, okay, try to go slowly. Okay, so this is like the definition. And also there is a characterization of these spaces more algebraic, that in terms of doing proofs is easily to deal with the next characterization, because as you can see, checking by hand these things by definition is completely, I mean, it's like it's very difficult to check every condition, right? But they provide an algebraic characterization that is more handleable, let's say. Okay, and this is the characterization. Is okay. Let me talk about more about this ring. It's like this is the class group. Here you allow not only Cartier divisors, also Veil divisors, and you consider all the global sections of all divisors, and you sum them somehow. This is the direct sum running from the class group. Okay, and these guys were able to characterize Mori dream space normal when the variety is normal, when this guy is finitely generated as a C algebra. Also satisfying this also technical condition, that this is somehow saying that the Picard is finitely generated, because if the Picard is not finitely generated, you cannot expect this to be finitely generated. So let me come back to the first condition. Is this one? Is this pick Y being finitely generated? And if this guy, the Cochrane, is finitely generated, you are dealing with a Mori dream space. Okay, and this is how I got involved in these Mori dream spaces, because these, as you can see in the corollary, are the natural station of toric varieties. During my PhD, I worked too much in toric projective simplicial toric varieties, and this guy looks like the natural extension of this toric, this kind of toric varieties, as you can see here. When this guy is exactly a polynomial ring, this is important because, how to say this? Here is important that the ring is being the polynomial ring, but it's also very important the way that you graduate the ring, right? It's like it's not the same dealing with P2 that with P1 cross P1. They are examples of Mori spaces, also toric varieties. Let's say the main difference is like if they share, okay, let's say P3 and P1 cross P1, they share the same polynomial ring, but the difference between the polynomial rings of these two guys is the way that you write the graduate the ring. Okay. After they introduced this foundational paper, Hugh and Keel, many people started to find many interesting Mori dream spaces besides story varieties, blow-ups up to some points. It was proved by Castraneva and Televet in 26. After Arcara, Bertrand, Koskuno, Isenga proved that log-Fano varieties that is somehow having some control in the cotangent space. and fixings of divisor. I'm not going to enter in that, but very interesting that the Hilbert scheme of points that people in algebraic geometry will know what I'm talking about. It's also a Mori dream space. Hilbert scheme of points on the projective plane. Okay, also Mori dream space. Grassmannians, for example, it was a surprise for me. And also the blowups of up to some points are going to be also Mori dream space. So if you want to keep in mind just to what follows for the talk, think about a projective space, a weighted projective space, a Grassmannian, and if you are familiar with blowups of some of these guys. Okay. So now I would like to show you how to construct Mori dream spaces when this class group is free using GIT theory, the geometric invariant theory. And then I would like to focus how to use these techniques in order to see Mori dream spaces as quiver moduli. Okay. So let me introduce the preliminaries for doing this. So assuming that my variety is a Mori dream space. Okay, so this guy here is finally generated. I assuming that this class group is exactly 0. And let's choose a presentation. Okay, so here there is a chosen, but as I said in the abstract, there is like a canonical way to do that. We'll discuss this later. Okay. Then having a gradient of this guy is going to define a semi-group homomorphism between n and z rho. How? You take a n-cup n-tuple, an n-tuple here, and you consider the variety. No, you consider first the polynomial with in these variables with powers the n-tuple that you choose here, and this is going to define an hypersurface in your variety, right? The zero locus on one polynomial is going to produce an hypersurface or a divisor, is something that is codimension 1 in your variety. And I am assuming that these guys are the basis of all divisors, so I can find a way to write down that hypersurface, that divisor, in terms of these guys, and this is going to be the image here. Okay, I hope this is somehow clear. And this also show you how it is going to act, this torus, in this affine space. This affine space is indeed Cn, the spectrum of this guy, but I like to keep it as An because keeping in mind this is an affine space. Okay. When you do a GIT quotient, somehow you want to remove some unstable locus, some unstable points. That and this is the way you do that. It's like if you choose something here in the dual of the terms, that is exactly the class group. Okay, you remove all the guys that when you send this under this degree map, you get a multiple of the divisors you started with. Okay, this case she. When you remove that, you are removing all the unstable locus, and you make the quotient, you get a proper geometrical object. Okay, as is written here. And moreover, as Hugh and Keel proved, there is a way also to construct the Mori dream space you started with as also a GIT quotient. Okay, because if you take this AN, you remove the unstable locus, and you take the action of the torus, you get a toric variety where the Mori dream space that you started with is embedded. Okay, so far the things like I have shown you is how to given a a Mori space, how to embed this guy in a toric variety. This embedding is somehow different from being projected, let's say, because as you can see here, you are respecting the action of the torus, and moreover, you are respecting the dimension of the class group, as it says here as a corollary. It's like all the runward reflexive chips that this in this case correspond to veil divisors, no Cartier veil divisors. You can get all the divisors you started with in your monitoring space as a restriction. Okay, so all the divisors are coming from the ambient space. And for me, this shows like projective toric varieties should be the new projective spaces, in the sense like it's the way it's the ones like you are. If you have a variety, you should look for a toric variety you can, not only a projective space, a toric variety you can embed it. In this case, this embedding respect the class group. And this will allow us to construct more green spaces also as quiver moduli. I will discuss later. Okay, I don't have too much time. Here, there is another way to construct. Another interesting thing of toric varieties is like they have many different approaches. Even you can approach them as a differential pure perspective, also as a, let's say, numerical perspective, as described in here, as a fan. I'm not going to enter in more details about this because I don't have too much time. Okay, but here is just another way to construct toric varieties coming from the fan. As you can see, it's on, here, it's very important. This is free abelian group. So how you can think about this as a lattice, and integers are integrals in that sense. So it's very numerical. Here are two examples of, one is a weighted projective space that is singular. And in this case, the singularity is a toric curve, as is described here. And the other one is something like, it's very familiar for all of us, but with the distinction that it has Picard or class group with rank 2. Okay, so there are many, this is a threefold, there are many surfaces that for me, the right embedded is not, let's say, in a P4 or P3, is in this guy if the surface has Picard number 2. Okay. And this is a way also to construct the unstable, having this fan, this numerical setting. There is a way to construct the unstable locus coming from the irrelevant idea that, for matters of time, I'm not going to enter too much in all these details. But what is important here is what is a quasi-smooth intersection variety in a toric variety. And somehow this is like of being complete intersection in a projective space. Okay, it's like it has, as usual, right, the same the number of generators coincides with the codimension of the variety, or in this case can be empty when this, remember, is the you are removing the unstable locus. So maybe just this variety just lives in the exactly in this unstable that you remove in order to get something, a geometric object doing GIT. Okay, here you can see like the also the feeling of these guys in terms of differential geometry. It's like these guys only detect, are somehow the ones like detect the singularities, but only singularities coming from the ambient space. Because remember, this guy in principle can have singularities as the weighted projective space that I mentioned before, P1122. So this has this feeling, differential geometrical feeling. Okay. Here is like my first contribution for this theory, but this is a very strong condition. I asked like for a self variety, asking for generality. Somehow I I guarantee this guy is going to be quasi-smooth intersection, asking for this general, this very generality. I will talk about this later. And I put this strong condition, like the ideal shape of this guy is going to have H1 cohomology vanished for all classes in the class group. If you are in that situation, you guarantee that the variety is a Mori during space. Okay, but somehow this condition is very strong. So but there is a way to guarantee this if you put, if you ask for conditions in the toric variety, for example, asking for all the divisors having a BNF, that means like they intersect with every curve positively, okay? And in these cases, you also are facing a Mori-Grimm space. This, again, this generality guarantee this is quasi-smooth intersection, and also in the proof is very important and is crucial because you use what is the Netter-Lefschetz theorem and the Grothendieck-Lefschetz theorem, that being general and having dimension d greater than 3 is telling you that this guy is going to have the same class group that the ambient, and when it's a surface or it has dimension 2, being very general guarantee also the same. That in the proof is a very key point. Okay, this is like the role of this generality and very generality in the assumptions of the proposition at the corollary. An interesting remark is that the only one-dimensional Mori-Grimm space is P1. This is why I always assume these conditions on the dimension, because you cannot expect even putting generality. If you are in a curve, being Mori-Grimm space is just P1. You don't have too much options there. Okay. Okay. Now, keeping all these things in mind, the rest of the talk I would like to focus in. Now I know how to produce, let's say, Mori-Grimm spaces. Following now the ideas of Crow and Wynne, I will show you how to construct Mori-Grimm spaces as fine modular of quiver representations. So I will start defining what a path algebra is, like in which kind of quivers very interesting in. One of the main things is like the vector dimension. The ones like I'm familiar with quiver representation is always 1, 1, 1, 1, 1, 1. So it's like if you have a quiver representation and you put the condition the vector dimension 1, 1, 1, 1, somehow you are dealing with a toric variety. Okay, this is so. Let me introduce the preliminaries. Let Q be a finite connected quiver with vertices Q0, arrows Q1. And these guys only tells what is the head and the tail of the arrows. Okay. The characteristic functions are going to form integral bases for the vertex space and the arrows space, respectively. A non-trivial path is just like a composition as you compose functions, like respecting like the head of one has to coincide with the tail of the next one. This is the way that you produce path, and the path algebra is just you consider all the possible combinations that are going to be okay. All the possible combinations of the path algebra. These are going to be a vector space, and then when you multiply in order to give it the structure of algebra, is like concatenation. It's like see exactly the head and the tail of the paths you want to multiply coincide. You just concatenate, and otherwise you just put 0. So it's a path algebra considered like all the possible paths you can construct from a finite connected quiver. Okay, so more definitions. A quiver is a cyclid if every cycle is the trivial one, just for every vertex having a loop. A source is not the head of an arrow. A spanning tree is a connected acyclic subquiver whose vertices coincide with that of Q. And a spanning tree has a root in I if I is the unique source of the tree. Okay. Here is it's like the way that I imagine quivers or representation of quivers is like the ones like are going to play the role of an ambient space are the ones that don't have relations. But if you put relations of how they are going to represent sub-schemes of on the moduli of quiver or representations. So our relations are you consider paths like they share the same head and the same tail, and you start to consider like combinations in the complex numbers of all these guys. Of course, everything finite. Okay, this is a relation, and if you consider a quiver, the set rho relations, is that going to produce an ideal in the path algebra? And these two guys form as is known as a bound quiver. Okay. Now, uh, I would like to explain how, given a collection of the sig-like bundles, you can construct a quiver. Okay. And the way to do it is like this. You have, let's say, R plus one line bundles that remember that for the construction of the embedding of every Mori space in a project in a toric variety, all these guys are coming from some reflection one chips that are the guys here, and all of these guys are going to represent a vertex. And the way to construct a arrow between these two vertices is like this. If there exists an irreducible section between these two guys in this way. There is a canonical isomorphism here between home of EI and EJ. And this is the way you construct the arrows, okay? And Crow and Smith proved in 28 that the quiver of sections Q is connected acyclic, and zero is the unique source. It's important here, zero, most of the time, this is zero is the structure shift. This is the structure shift. And also with this, you guarantee that being this guy effective, you guarantee this always, at least there exists an arrow from the structure shift to the line bundle you are dealing with. Okay. Here there are some examples. A trivial one for P2, choosing this collection of line bundles. Is there a problem with the sound? Or everything's okay? Okay, let's continue. As I just said, represent the vertex, and this is the way that you construct the arrows. Okay. This one is more interesting. I took these pictures from Wing's thesis. He was a student of Crow. Yeah, and I think you cannot do this by hand. Maybe using Macaulay too, or but the interesting part is at least exists a way to represent every Mori dream space as a fine moduli of quiver or representations. Okay. Also, you have to be careful with the light bundles you are choosing, as you can do. It's the same role or the same game you play when you are taking some divisors. If it's samples, if it's net, right? You are looking for something like, let's say, it's very ample that allow you to really make an embedding of your variety into a projective space. Is the same problem that you face here. Okay, and here is the way to consider bound quiver sections. It's like somehow how to give relations. Like if you have, and this is the way here, considering this two-side idea. It's like you consider all the finite set of paths with the same head and the same tail. That is somehow is very related with how you construct relations given a quiver, and you just focus in the ones like lives in the ideal with the Mori space that you started with. Okay, and this is going to produce a bound quiver of sections. So given this collection of sections, you represent a quiver, and also given a Mori space, you know how the relations of the bound quiver is associated to the Mori dream space. Okay, this is a technical result. Okay, I'm not going to enter too much in this. This is important. This is what a representation is, right? Is for a representation of a quiver. It consists of a C vector space Wi for each vertex, and linear maps between this vertex. You can put in principle any dimension, but if you want to get a toric variety, as I said before, think about representations that have vector dimension 1, 1, 1, 1, 1. Okay, we will be more clear in some slides more. Oh my God, don't have time. So this is like the equivalent. I think it was introduced by Keen. This is like the equivalent of being semi-stable, like the equivalent of the GIT. And also you have to remove some things like you don't like in the some instability. Let's say when you want to construct a space coming from these representations. So I don't want to enter too much in this. I don't have too much time. Okay, but as you can see here, it's the same feeling of the GIT construction, right? But here is just in terms of representations, right? So from one side, you have the GIT coming from the Mumford theory, and this is like coming from Keen's theory. And somehow they match, as I will show you. There is a special way that you have to choose. This special way is somehow telling you what is going to be the semi-stable points in your construction, or the stable points. Okay, and here is a very important result. It's like if you have a quiver which is finite, connected, acyclic, with a unique source, okay, when you play this GIT construction of the representations, you get exactly the same as if you remove the irrelevant ideal of the quiver, and also, a more important, you get a finite modular space of theta stable representation of the quiver with dimension vector, as I said, 1, 1, 1. Okay. This is for me a very interesting way to see a toric variety, another construction of them. And when I saw this, my purpose was trying to see if I can construct also hypersurface or quasi-smooth intersection objects in terms of moduli of quiver representations. Okay. Here is like, as I said, that having a multi-grade linear series is the way to make embeddings keeping track of the class group. Okay. Okay, here are too much technicalities on how all the actions of the groups are respect from the GIT construction, from the King's construction, for the moduli of quiver representations. Okay, still 10 slides more. Here is like, again, the equivalent of, but for multilinear series, like if you have effective divisors, the most you can expect is a rational map. This, for people that is not coming from an algebraic geometry background, this means just as is defined in an open Zariski subset. And you remove these Dutch arrows when you can define them off completely. But for doing that, you have to ask for more to these line bundles. okay, that is here. When you have a collection of disease based from field line bundles with quiver 6, then the image of this guy is this. And if you ask for very ampleness of every of these, you get a proper morphism. It's well defined in the complete variety. And okay. Here, bound quiver representations. Here it just appears. So far, we have seen how a representation of a quiver is, but also you can make sense of what about quiver representations is, given giving meaning to how to, in terms of representation theory, to the relations of inside the pod algebra, what is just here. Let's Bj, a two-side ideal of relations with the generators of the form finite paths sharing the same head and the same tail. A representation of this guy is something like respect somehow, as you can see here, is like being orthogonal on one way. Okay. And with this, you can construct this idea that somehow tell you exactly where you find the points, like are exactly a representation of the ideal of relations. Okay, now we have here how to produce a modular space, find modular space, not only for a quiver, but for a bound quiver. That's, as I said to you, is this guy represent a subscheme on this moduli of quiver representations without relations. And again, this is crucial because this is going to guarantee we are dealing with a toric variety. Here more technicalities. I'm not going to enter this. Okay, I will focus more in this. This is the main theorem of Crow-Wing. Okay, so we started with a Mori dream space, and Hugh and Kiel were able to embed this Mori dream space in a toric variety, a projective toric variety that respect the class group. Then Crow and Wings explode. They somehow relate to the collection of some line bundles in the class group, a quiver. And they were able to construct this toric variety as the quiver moduli of representations without relations. And then they found the necessary and sufficient conditions for this guy to be embedded as a quiver moduli. Huankill give you the embedding without thinking about quivers. And then Crow and Wings came with the idea of represent this as a quiver moduli, and then as this as a sub-quiver moduli, and see what are the conditions for this guy also be a subskin of this guy, and so how this diagram making commute. And the technicalities are the saturation of this ideal and asking for the collection being very ample, as is written here, being distinct and base point free. And yeah, this is the main result of Crow and Wings. And I use this in order to see what happens if I intersect two Mori dream spaces. So my idea was, I have a Mori dream space with I started, then I construct the toric variety, and then I see how to construct more Mori dream spaces here in this variety and see how they intersect with the Mori variety, with the Mori dream space that I started with. And this is written here. This is like my next contribution to the theory. And it's like I have two guys that I can represent respect to the same toric variety as a quiver moduli. If this guy is a Mori space again, then I be able to construct this guy as you expect, right? Like just the sum that is going to represent the intersection, as if you are familiar with Nustellan's Hilbert theorem, is somehow the equivalent of that in the way, like if you have the sum of ideas geometrically, you are representing the intersection of the varieties. Okay, and besides the proof is somehow something like they use here to construct, to guarantee the isomorphism that is hidden in this saturation idea. Okay, how much time I have? Oh, I have 2 minutes more, so I didn't have time. So, and as I expected, I didn't have time to enter to the Hodge numbers, but in my thesis, I knew how to, when this is quasi-smooth, I know how to put here a natural Hodge structure coming from the ambient space, and also how to compute, or at least to find isomorphism to this guy related with the something that is called the Jacobian ideal, the Jacobian rig that is very related with the Jacobian ideal. And this is the things like as we can hear, but I don't have more time. So it's here. It's okay. It's here. This is given a. So somehow here I was able to find a way to construct the intersection of 2 Mori spaces as quiver moduli, and all these isomorphisms are algebraic, so they are going to respect not only the Hodge structure, but also, let's say, the algebraic Hodge structure, like the guys, the okay, I don't know how to explain this rapidly or without too much time. But okay, when you consider the cohomology of these guys, there is a way, thanks to the Poincare duality, the algebraic objects here are going to represent sub-objects in this cohomology. And this is what I mean for the algebraic cohomology, right? It's like some objects inside this guy, when they are algebraic, they are going to be part of this cohomology, right? And under suitable conditions, you can tell exactly when all of them are coming from the from in that way, from algebraic subvarieties. That, for example, is the case here, as I say here. That means even to be that the Hodge conjecture holds. It's like you can describe somehow the all the middle part of the cohomology are precisely described for all for the subvarieties with the proper codimension. Yeah, it's the last thing that I can tell. Yeah. Thanks for the attention.